Hello, students. Welcome to the first content video of the year. We are going to start Unit 2, Limits and Continuity. So you may or may not have done limits in pre-cal. You certainly have heard about continuity before now. Now, this is Mr. Davis and myself and Mr. Chase, who now is the part of Mr. Chase is now being played by Mr. Schuler, who is just about as tall as Mr. Chase. Not quite, but almost. Anyway, notice the pool noodles that we are holding is a continuous function until here. And then there is a discontinuity. Okay, so if you probably should take notes on this video as maybe title your notes Unit 2, Limits and Continuity 2.1, or the beginning, day 1, however you want to talk about it. All right, so the idea or concept of a limit. So this is the limit notation. And what's underneath the C value is a domain value, and you read this, the limit, as x gets really, really close to some domain value. F of x, or my graph, gets really, really close to something. So I want you to think of a limit as function behavior. So this equal sign doesn't really mean equal a number per se, even though sometimes L will be a number, sometimes it will be an infinity, but I need you to think of this as a range descriptor. So this is saying the limit is what behavior does my function have as my domain gets really, really close to some value, right? C is an X or a domain. L is a Y or a range value. But remember, it's more, I shouldn't say value, I should say descriptor, right? Because even though we use an equal sign, it really is an adjective. So when I say the actual value, when you plug C into the function is irrelevant, that's really a strong statement. But what I'm saying is that when I give you a function and I say, what is f of 2 in your function? And if you tell me f of 2 is 5, that means there is a point on the graph where when x is 2, y is 5. And that point exists and it makes the equation true. That is related to what a limit is, but a limit is more about what's happening around 2. So when the domain values are close to 2, are the range values close to 5, or are they something else? Okay, so I kind of think of my little clouds. So when I am evaluating a limit, though, I do plug and chug first, right? Step one to evaluating a limit is to plug in. The default mode is to plug in, right? And see what is the function at the value of C. And then I'll worry about what it is close to C. So for example, when I ask you, what is the behavior, right? What is the behavior of the function 2x plus 1, which is a linear function with a slope of positive 2 and a y-intercept of 1, as the domain gets really close to 3? Well, regardless of, I know what happens exactly at 3, right? If you plug 3 in here, 2 times 3 is 6, plus 1 is 7. When x is 3, y is 7. But the function all around, because of the behavior of a linear function, the behavior of the function all around where x is equal to 3 is pretty darn freaking close to 7. That's the idea of a limit. If your function is a well-known, behaving, continuous function, then even though I said the actual value is irrelevant, if your function is continuous, then the limit is equal to the plug and chug, right? For exactly the reason I talked about, right? When you plug in 2.9, you get something really close to 7-ish. When you plug in something close to 3, you get something close to 7, right? I don't know if it's exactly 7.1, but you get the idea, right? So everything, the range, as you get close to 3, the ranges are close to 7. And that's all I want for a limit. I want to know what's close, right? So there's a picture of my function as I've been drawing. There's the 0.3 comma 7. So I want you to think about as domain values, you plug in close to 3 from both sides, both the right and the left. I want you to kind of think of these range walkers, right? Here's a range walker. And I want to know if their bellies bump. I don't care if their feet touch, but I want to know if their bellies bump, right? So as you plug in numbers close to 3, your range walker is going to walk here. As you plug numbers in a little bit bigger than 3, but close to 3, your range walker is going to be up here. The question is, when they come closer and closer to one another, will they bump bellies? They do, and the level, get it, L, the level of the bellies is 7, which happens to be the exact same value as the function. But that's because the function behaves really, really nicely around 3. Continuity important. So look at this function. This is a piecewise function that has a hole in it, right? The function behaves exactly like 2x plus 1, except at 3, right? At 3, the function value is 0. But this is why I said the value of the function at c doesn't matter, because f of 3 is 0, right? When x is 3, y is 0 by the definition of this function. But I'm not talking about 3. I'm talking about being really, really close to 3. When you plug in a number like 2.9 or 3.1, you don't get a range value close to 0. What do you get? They still bump bellies, right? I don't care that their feet would fall through that hole. Their feet aren't touching, right? The range walkers, the limit is still 7 because the level of the range walkers is at 7, right? So a limit is not asking you for the function value. They happen to be the same if you have continuity. But if you don't have continuity, you need to see what's happening around the function value, right? So what's going on around 3? The level that both range walkers are at. The left range walker and the right range walker bump bellies at a level of 7. That's what a limit is. The actual value of the function is irrelevant unless you have continuity. Psst. Unless f of x is continuous. That's why continuity is important. If your function is continuous, then the behavior around the function value is the same, is very, very close to the function value. That's why we love continuous functions. So let's look at this question, right? So I don't have, this is the graph of f of x, right? The graph does not exist to the right of 3, so I only care about the range walker coming from the left. The range walker, as you plug in numbers like 2.9 and 2.9999999, the range values are getting really close to what level? 3. When you're at 2.5, when you're approaching 2.5, now 2.5 is in the middle of the domain. So I have to look at the range walker from the right and the range walker from the left. This time I need my bellies because I don't care about the actual function value. I care if they will bump bellies. And since I am just reading from a graph, I can approximate. Don't give me 10. Don't give me -2. Don't give me 0. 2.5, 2.4, 2.6, whatever you want. 2 is also in the middle of the domain, right? This was at the end point of a domain, so I only cared about the right. Remember, here 2.5 is in the middle of the domain and 2 is in the middle of the domain. So I have to have a left range walker and a right range walker. Notice the function f of 2 is equal to 1. F of 2 is equal to 1. But the function value isn't what I'm asking. I'm asking about the function values as you approach 2. So I have my blue range walker here and my blue range walker here, and they are walking along the range, and they're not going to step on 2, right? The domain is not going to be 2. Domains are 1.99999 and 2.00001, and the range values that go with that are really, really close to 2, right? Level. The level of the range walkers, not at 2 necessarily, around 2. So plugging in numbers around 2 give me levels around the y value 2, even though the function level is at 1. So think about with your algebra brain. There's lots of functions that you should know that you can just plug and chug into. When does the function value equal the limit? When you have continuity. So polynomial functions have a domain of all real numbers. They are continuous. Bumping bellies is never an issue. Plugging in f of c will always give you the limit. You're just giving me a range value. Rational functions are a ratio of 2 polynomials. You have an issue. But your issue, your continuity issue, is when the denominator equals 0. Otherwise, you plug and chug. Algebra, plug in. But if you have a bad x, a number that makes 0, if your x is, or your c, I'm sorry, is a number that makes the denominator equal 0, you've got an issue. Trig functions, sine and cosine, no problem. No problem. Sine and cosine are continuous over the domain. Bumping bellies is never an issue. F of c is the same. Plugging in c, plugging in the range will be the limit. I have issues with tangent, cosecant, secant, and cotangent, but only where they're broken. That's why you're supposed to know where these functions are broken. Everywhere else in their domain, right? I don't have any problems. I can plug and chug. Now, I haven't told you what to do about when you have an issue. Issue for rational functions when the denominator equals 0. Issue for trig functions when you have tangent, cosecant, secant, or cotangent. Denominator equals 0 causes a discontinuity in rational functions. Tangent, cosecant, secant, and cotangent all have discontinuities. Exponential and log functions, right? Exponential functions have a domain of all real numbers and are not broken at all. So there are no issues with exponential functions. You can just, your range value will always be your limit. Log functions are continuous once their domain starts. So I'm going to graph the exponential function. Bumping bellies, never an issue with exponentials. With logs, bumping bellies, never an issue once the domain starts. No issues once domain starts. And what I mean by issues is continuity. If you're continuous, you just have to give me the range, and that's the same as the limit. Exponential functions, no issues whatsoever. Absolute value functions, no issues, right? Absolute value is continuous. Radical functions. Remember from your Algebra 2 and pre-cal experience, even radicals, so the square root of x, the fourth root of x, and so on and so forth. No issues once the domain starts. The range is the limit. Odd radical functions, blah, 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 no issues at all. No discontinuities. Okay? So look at that. All these things I studied in Algebra 1, Algebra 2, and pre-cal help me with limits because I know the function behavior, I know where I know what the domains are, and I know whether I have any issues or not. So what do I do when there are issues? All right, before I even get to what to do with tangent or what to do with rational functions that have discontinuities, holes, or vertical asymptotes, let's look at this function. This is called the greatest integer function, or the step function is also a name for this function. There are closed circles on the left side of each step and open circles at the other on the right end of each step. The greatest integer function says that you have to, let me make a chart here. The greatest integer function says that when you put in an integer, you get an integer back. But when you put in a non-integer, you get the range is the greatest integer you already wrote down. The greatest integer I already wrote down. But as soon as I get to the next integer, the range value is an integer. So that's what you see here, right? When x is a half, the range value is 0. But when x is 1, the range is 1. So what happens as when I want to know as x approaches 1.5, right? As x approaches 1.5, I have to get out look at my range walkers. Here's 1.5. I have a range walker here and a range walker here. And as I plug numbers in really close to 1.5 from the left and the right, my two range value guys are at a level of 1. But what about this? What about at 2? As I approach 2 from the left, purple range walker is here, left purple range walker, and as I approach 2 from the right, there's my range walker. My range walker girls are at different levels, right? Left level is different from right level. Left range walker as you approach 2 from the left. Right range walker as you approach 2 from the left. From the right. They can't see one another because their necks don't bend. If they can't see one another, they certainly don't bump bellies, and therefore the limit does not exist. You can write undefined, it's just AP won't, they understand that language, but they'll never write undefined to you. They will write DNE for does not exist, which means no bumping bellies. When you are asked for a limit inside a domain, you must approach 2 from the left and the right. And if your range walkers don't meet, they don't bump bellies, then the limit does not exist. But check this out. This limit does exist and is 1. This limit exists and is 2. Can you figure out why? I wasn't asking you about bumping bellies. I just said, what's the behavior to the left of 2? How does the function behave to the left of 2? What level is this range walker at? This range walker is at a level of 1. But what is the behavior of the function as x approaches 2 from the right? This range walker, as I approach 2 from the right, this range walker, her feet are at a level of 2. Notice that when the behavior at the left does not match the behavior from the right, the overall limit does not exist, and the graph behavior has a discontinuity. That didn't happen at 1.5, right? If you notice at 1.5, if I asked you what is the behavior of the function as you approach 1.5 from the left, from the left, the range walker was at a level of 1. As you approached 1.5 from the right, the range values were at also 1, right? And again, let me go back to the table. As you put in numbers close to 1.5 from the left, like 1.4, you had a 1. 1.49, you got a 1. 1.5, you also got a 1. 1.51, you got a 1. 1.501, you still got a 1, right? Because it's the greatest. So all of these range values are 1. So the overall limit is 1. But when I make a table for the greatest integer values around 2, when I put 1.9, I get a 1. 1.99, I get a 1. 2, I get a 2. 2.01, I get a 2. 2.001, I get a 2, right? Notice that the left and right values are not the same. There's a discontinuity. Therefore, the overall limit does not exist. So we just showed a theorem. The limit as x approaches a domain value of a function is a level if and only if, I didn't misspell this, it's if and only if the left behavior of the function is that same value and the right behavior of the function is that same value. Only when these two values match does the overall limit exist and is that same level, right? So they call that the left-hand and right-hand limit. If the left-hand limit equals the right-hand limit, then the overall limit exists. Here are some properties of limits in your textbook or your textbook PDF, page 61. These properties of limits, you will never have to repeat. You'll never have to spell them out. No one will say, what is the product rule for limits? But you do need to know that you are using you'll use the properties of limits even when you don't know the properties of limits. For example, when I gave you the limit as x approaches 3 of 2x plus 1, we were actually using the sum rule and the constant multiple rule. This is actually the limit as x approaches 3 of the constant function 2 times the limit, 3, as x approaches 3 of the function x plus the limit as x approaches 3 of the constant function 1. I swear sometimes these problems give kids more trouble than more complicated functions. But let's again think about let's think about these limits graphically. Here's the graph of y is equal to 2. Continuous function. What is when x is equal to 2, what is the range value? I'm sorry, 3. When x is equal to 3, what is the range value? 2. So this limit is 2 times the limit of x. I'll draw that one over here. This is a continuous function. When x is equal to 3, what is y? 3. So I just evaluated limit 1. I'm going to multiply times limit 2, and I'm going to get 6 plus the limit of the constant function 1. So let's pretend this is the constant function 1. When x is equal to 3, what is the value of the function? 1. The limit is 7. Okay, so this just says that you can look at a function that is a combination of multiples or sums or differences. The limit of a sum is the sum of the limits. The limit of a difference is the difference of the limits. The limit of a product is the product of the limits. The limit of a constant times a function is a constant times the limit. The limit of a quotient is the quotient of the limits, given that the denominator does not equal 0. Again, you're going to use these properties so much, you're not even going to name it or think about using it. Yeah? Okay. Before I get to this next kind, before I get to these AP ones, I want to show you an issue that we can fix. So before I do this one, I think I hid this slide and I didn't really want to. What if I ask you about the limit of okay, I have an issue. This is a rational function, and remember I told you rational functions have you don't have to, you can just plug and chug unless this number makes the denominator 0. Well, guess what? 2 makes this denominator equal to 0, doesn't it? So I have an issue. If I plug and chug, I get 4 over 0, right? Uh-oh. So if I can't plug and chug, go to algebra. Simplify. Whoops, sorry. I wanted this to be a minus. I was like, wait, that's not going to work. X minus 2. So I'm going to end up with 1 over x plus 2. Right? Replug in. This function here, simplified function, behaves exactly like this function, except at 2. Plug 2 in now, and you get 1/4, which is the level. What that means is this function has a hole. I don't know exactly what this function looks like, but at 2, there is a hole, and the level of the hole is 1/4. And the function, whatever the function is doing around 2, I don't know exactly what this function looks like, but as you come to 2 from the left and the right, the function is not defined there, but because this factor canceled out, x minus 2 canceled out with x minus 2, I know that the whole exists at 2, the level is 1/4, and I only care about the level around 2. We're going to do more like those in class, so don't worry, but I wanted to show you one example before we got to class. And then the last thing I wanted to show you is an AP. AP loves this problem. I don't know why, but they just love it. And I see it all the time. Notice I have an issue, right? Because I tried to plug in 0 here and here, and I got 0/0. I don't care that the numerator is 0, but the denominator is equal to 0. Uh-oh. There's no algebra. Like that last problem I showed you, I could get around the 0 in the denominator because I could... All right, I'll be there in a minute. I could factor and cancel. I can't do that here. There's no canceling. Don't you dare tell me you can cancel those x's. Here's what that function looks like. There is a hole at 0. Do you see that? When I plug in 0, there is a hole. But talk to me about the range walkers as you approach 0 from the left and the right. As you're around 0, the level of the function is very, very close to 1. So this is a picture of something called the sandwich theorem. We'll talk again a little bit about this. The red function is sine x over x, and it is between sine x and the constant function 1. And that is a proof behind why this limit is 1. You do not, the sandwich theorem used to be part of the curriculum, but it isn't anymore. So I just put this picture up here just to, I don't know, just because I missed the sandwich theorem. But this ratio, or ratios like it, show up so often, I wanted to make sure to highlight it to you. It is a pattern that is worth memorizing. If you're going to 0, you have a ratio of sine x over x. That limit is 1. This isn't quite sine x over x, but I'm going to tell you that this limit is 1. I'm going to tell you that this limit is 2, and I'm going to tell you that this limit is 2/3. Do you see the pattern? As long as you're going towards 0, and you're in radians, by the way, I can graphically show that this limit will always be the ratio of the coefficients. I'm going to leave this last problem for us to do in class because this problem has a sine x over x in it, but it takes some algebra 1, and then it takes some properties O limits to rewrite, and then you will be able to evaluate that limit without a calculator. But that's some of the stuff that we'll do in our live session. Right, can't wait to see you then. I gotta go eat my dinner because everybody's calling me. Bye.